Bismillahirrahmanirrahim. Welcome to lecture number 9 of deep learning. The topic we will cover is bias and variance. These are the discussion agenda. These are the topics that we will cover. We will discuss train, dev, test sets. We will discuss mismatch test set problem. We will discuss bias and variance. And we will see basic recipe of machine learning to deal with the problem of bias and variance. So this is a train, dev, test sets, setting up your machine learning application. So we have discussed that in neural network, and particularly in deep neural network, there are many hyper parameters like number of layers or number of hidden units or learning rate and activation function and many others like the number of units per hidden layer, the activation function like sigmoid function, softmax function, 10H function. These are different activation function and many others like if you are using gradient descent with momentum, you have this parameter beta 1, beta 2, RMS prop, there are other parameters. So the more complex network you are making, the more hyperparameters you are playing with. And this machine learning or this deep learning is used in different types of problem, like it is used in NLP. In NLP we talk about RNN and we use these deep learning network. In computer vision we use deep learning network. In speech we use deep learning network, and also in structured data like ads or search or logistic regression or many other problems. All these problems, they are using deep learning framework. They are solved through deep learning algorithm, and because of this, all these different communities like NLP, computer vision, speech recognition, structured data algorithm, all these they are using deep learning technique, and because of this they are becoming closer to each other. So this is a very iterative process. You get an idea, you code it, you experiment with it, then you get some analysis, you get idea how to further improve it, then you code it again, you experiment, you analyze, then you get more intuition about the problem and you know how to further improve the problem. So this is very iterative process, and different number of parameters are involved that we have to test the model and see the performance of the model. So traditionally what we did, we had, let's say we have a data of size, let's say 100. So training test we take 60, dev set and test set. The difference between dev and test set is for the dev, it's like the hold-out cross validation. Sometimes it is called development test. So what happens, we train, we get some analysis, we check the model on the dev set, we get some intuition, and then we train again. Then we check it on dev. So this is iterative process, and at the very end, when we are sure that our model is working perfectly, so then we go to the test set and see the performance of the algorithm. So previously 60-20-20 rule, some algorithm they were using, or sometime only train and test set. So 70% train and 30% test. But normally these domain were only like 100 or 1000 or 10,000 samples. So that's why we were using this strategy. But in the context of big data, when we have millions of samples, so this rule is not maybe necessary anymore. For example, if we have 1 million So 30% of 1 million is 300,000. 300,000 is a lot of sample to exclude from the data. So what we do in the big data and in the deep learning context, we use 9811. So if we have 1 million, so 1% of 1 million is 10,000, and that's enough to test your algorithm. So 10,000 for train, 10,000 for diff. Or even in some cases we get more, 99.5 when we have millions of samples. So 99.5 we take as training, 0.4 maybe we take as div, and 0.1 as test. So these things are changing in the deep learning era. There is this problem of mismatch train test distribution. So assume that you have a training set where you have cat picture from web pages, and dev test sets where cat picture from user using your app. So this is a different distribution, because on the web page maybe there are some blurry images, or the quality is not very well. Actually on the internet the quality is very good, because these images are taken by professional cameras, and they are using enough lighting to capture images. But if you take image from your app, maybe it's blurry, maybe it's not clear, or maybe the rotation, or maybe most part of the cat is occluded. So that makes it complicated, that makes a mismatch. So what we have to do, we have to make sure that div and test set come from the same distribution. So when we have train and div, so the data coming to the train must also go through the div. So if we take only a training set from the web pages and div and test set from the app, so it's not going to be very accurate, because we are training in one domain and we are testing in a different domain. So that's very important, that you make sure that the distribution is similar, like both of these data are included in the train, and both of these data, or these pictures, are included in the div. It's also possible not having a test set might be okay on the dev set. It's also used in different literature. They are using only div set, not test set. So let's try to understand bias and variance. So let's take this image. We have two different classes. One is cross, one is circle. And if we try to make classification, maybe we make this blue line. This is x2 and this is x1, and based on these two features we make these two classification. So this is what I'm using, logistic regression, a simple logistic regression, and it make a classification like this. You see this circle is on the is in the group of the crosses, and similarly some crosses are mixed with the group of the circle. So this is what we call underfitting. The logistic regression is able to distinguish between two classes, but it's not very accurate, and it's just a straight line. On the other hand, if you look to the extreme right graph, we see that all the instances are classified. I mean, the same classification, the same technique, are all the instances of the different classes, they are grouped together. Even this circle, you see the line is going very inside, and then it is coming outside, and then you see it is trying to distinguish between this sample. So all individual samples are classified. This is what we call overfitting. Now what's the problem here? The problem here is accuracy is very low, right? Here accuracy is very high, but here generalization will be very low. For example, what if we have a circle here? Or what if we have a circle here? What if we have a circle here? So it will not be able to generalize well. This problem, accuracy is very low. So we don't want high bias, we don't want high variance, what we do, maybe we have a circle like this. Here one sample is incorrectly classified, this sample is incorrectly classified, but this is just right because it's easy to generalize when we have more samples. So we want to avoid high bias, we want to avoid underfitting, we want to avoid overfitting. And how do we know that this problem has overfitting or this problem has underfitting? So let's say we have trend set error and depth set error. So let's say trend set error is 1% and depth set error is 11%. So there is a huge gap between 1 and 11. So it means that our problem has understood the trend set, but it's not able to generalize to the depth set. So that's why we have high variance. If we look to this problem, the trend set accuracy is 15, the depth set accuracy is 16, so it's high bias. High bias means that we are not able to capture it's underfitting, because you see, even the training set we are not getting very good accuracy, assuming that the human error or the base error is 0%, because it's very easy to distinguish between cats and dogs. It's a very well-known problem and easy classification. So this shows that this is high variance. On the other hand, if we have 15% train accuracy and 30% test, so it's both high bias and high variance. So we don't want high bias, we don't want high variance. What we want is low bias, low variance. So let's say we have a problem 0.5% on the trend set and 1% on the diff set. So that's going to be low bias, low variance. We normally use this human error in case of images, or base error, optimal base error. So normally I told you that this is very simple classification problem, so human error should be approximately equal to 0%. So this is high bias and high variance. So if we draw this line, it is high bias. If we draw a line like this, only one sample it is distinguishing, so this is high variance. But if we have something like this, this is, I think, just right, low bias, low variance. Now, what's the basic recipe? Like what we need to do in case there is high bias and what we need to do in case there is high variance. So let's say first we check, is there high bias? If there is high bias, no, then we check whether there is high variance. If no, then we are done. But if there is high bias, so what we do, we may try bigger network, increase our deep learning network, maybe we train more layers, maybe we train our neural network architectural search, maybe we change different networks. So this is what different techniques that we can try, and then we go back and check again whether it is high bias. Then we check high variance. If it is high variance, so we can add more data. We can use regularization, which we will discuss in the next lecture, and we can also try an architectural search. So then we go back again and we check high bias, high variance. So the idea is we want to have a balance, like if we decrease bias, maybe we increase variance, and maybe if we decrease variance, its chances is that we decrease bias. So we just want to have a trade-off between bias and variance.